So, hello everybody and welcome to this operations research video lecture. We are now in chapter 5. So we have finished the octave with spice nodes, and this is the first chapter, although it's called chapter 5 of the nodes, the companion nodes, linear programming with spice. And in this chapter 5 it's titled Product Mix Problem Revisited. So yes, this is the chapter 4 of the octave with spice nodes revisited. So this is pretty much the same thing, but since this is a very essential part of this course, I will repeat the same stuff slightly differently here. Hope you don't get bored. Alright, so the first part here is modeling product mix problem, and yes, revisited. So we have the problem 5.1 here. This is the same Moore Dips Bakery problem as in the chapter 4 of the other notes, but it's presented here slightly differently. So what was or is the problem? We have Moore Dip Bakery that produces 3 types of Fremen cakes. The cakes are called Atreides, Corrino and Harkonnen. And each cake is made out of nutrient powders, and the nutrient powders are fat, sugar, protein, water and spice melange. And then the composition and the selling prices of the cakes and the number of available nutrient powders, they are explained here in a tabular form here in this table. So I think it's relatively obvious how you read this. So here on the columns we have different cake types: Atreides, Corrino and Harkonnen. Here in the rows we have the nutrients: fat, sugar, protein, water and spice melange. Then here in the margin we have the selling prices for each cakes, and in this margin we have the availability of different nutrient powders. So what is the problem? So kind of obvious that Moore Dip Bakery wants to maximize the daily revenues. Why not? That's what a business should do. And then what should Moore Dip Bakery do? Do precisely. Okay, so this is the problem. And what do we have to do first? We first have to model this problem mathematically, and then in the end we of course want to solve this problem by using a computer system some kind, and the some kind, well in this course it's the GNU Octave and its function glpk. And yes, in order to do that we have to first model this problem mathematically as an LP, and then we have to somehow explain this LP to GNU Octave, which basically entails us that we have to rewrite it in terms of matrices. Alright, let's start with the mathematical modeling phase. So we want to build or represent this problem 5.1 as an LP, that is a linear program or linear optimization problem. And in order to do so, we follow the three-step algorithm that was given in the chapter 4 of the previous notes, Octave with Spice. And yeah, let's repeat the algorithm here for the sake of completeness and for your convenience. So here is the algorithm 5.2, which I call optimization modeling. There are 3 steps. So the first step is to find the decision variables. So what are the actual variables that we can choose? So what is there to decide? Then there is a step 2, that's the objective, what we want to do. typically minimize or maximize something, and how this, what we want to maximize or minimize, that is our objective or objective function, how they depend or how they are calculated from the decision variables. And finally, step 3, this is usually the step where we have to do most of the work. We have to find the constraints. That is, in step 1 we didn't care about what we can decide, we only thought about what we can decide in principle, and here in step 2 then we look what we can decide in practice, that we look what kind of things constrain our decisions. Okay, and before using this algorithm let me just make a short point. Why do we have an algorithm like that? Why don't we just go and model? Well, of course you can do that if you are clever enough, why not? But if you try to do that, I mean you try to do everything at once, so you take the problem, contemplate a little bit, and spit out an LP. If you can do that, fine. And once you are experienced in this kind of business, you probably can do it, but at this point I think it could be a bit overwhelming. Indeed, the idea of this algorithm is that you do not try to do everything at once, and let me put this in other words, or actually Archbishop Emeritus Desmond Tutu's words. He said that, in a slightly different context of course, that there is only one way to eat an elephant, a bite at a time. So this is what we do. So our first bite is the step 1. I mean, usually it's the finding the decision variables is the most natural starting point. Not always, but usually. So that's the step 1. And again, we don't care if some decisions are practically possible or not. We simply want to, maybe this is the word here, we want to identify what we can in principle decide. Okay, so let's go back and look at the problem. So what is there that More Deep Bakery can decide? So what More Deep Bakery is doing? And well, here it says in the first sentence, More Deep Bakery produces 3 types of Fremen cakes. These are Atreides, Korrinen and Härkönen cakes. So what is there to be decided? Well, it's kind of how many cakes do you bake? Okay. And there are 3 types of cakes, so it kind of follows that we have 3 decision variables. And okay, we call these decision variables x's. It's a kind of standard in mathematics to call the unknown x. So this is what we want to solve. What are the decision variables? I could have, of course, used more descriptive variable names. Sometimes it's a good idea, sometimes not. In these notes I've decided to use kind of standard non-descriptive notation almost everywhere. So with this notation, x1 will be the number of Atreides cakes produced daily, x2 will be the number of Corrino cakes produced daily, and finally x3 is the number of Harkonnen cakes produced daily. Alright, so now we know the decision variables, so the first bite of the elephant is eaten. Let's move forward to the next bite, step 2, and so we have to find the objective function. And now, since we already have identified the decision variables, this is relatively straightforward. So what is the objective? So the objective is kind of given to us, so it's here. So the More Deep Bakery wants to maximize daily revenues. So yes, the objective is to maximize daily revenues. So what is the daily revenue? So it depends on, of course, the cakes we bake. And how does it depend on them? Well, it's given here in the bottom line selling price. So each Atreides cakes, More Deep gets 120 solaris, each Corino cakes 170 solaris, and each Harkonnen cakes 100 solaris. So what is the revenue? You just sum the total selling prices of all the cakes, and yep, here it is. Z is 120 for the Atreides cakes times Atreides cakes, 170 times the Corino cakes, and 100 times the Harkonnen cakes. And again, small note, here I use the letter Z, which is typical in LP to denote when you have a maximization problem, especially sometimes also for minimization problem, so the objective function is called Z. Of course, it could be called anything, and we could have again used a more descriptive name like revenue for it, but well, let's use a standard name Z. So whenever you see a Z in these notes, it almost always means that that's the objective function, and usually it means an objective function to be maximized. Alright, so we are getting a lot of elephant. So finally the third step, where we really eat the scraps of the elephant, is the constraints we have in this problem. And what are the constraints? And maybe now it's actually good to really come back to this problem and look at the table. So all the data of this problem is actually in the table now here. So what are the constraints? So what do can we make any number of Atreides, Corino, and Harkonnen cakes we like? Well, no, because we make them out of nutrient powders, and we do not have unlimited amount of nutrient powders. So nutrient powders, they are a scarce resource for us, and the limits, or actually the availabilities, they are given here. So for example, let us look at the fat powder here. So we have 100 kilos of fat, and each of these different cakes take a different amount of them. So if we make, well, it's called x1. x1 is the number of Atreides cakes we bake. So each cake takes 70 grams of fat powder, so x1 times 70 gram is the amount of grams we spend on Atreides cakes. Similarly, for Corino cakes, it's x2 times 50 gram, and Harkonnen cakes, it's x3 times 150 gram. So if we sum them up, then that's the total amount of fat powder that is used in the cakes that we are producing. And well, this cannot exceed the amount of fat powder we have in total, which is 100 kilograms. So this, what I just explained, is what we have here written in this line. Okay, we have written 70 times x1 instead of x1 times 70 grams, which is of course the same thing. It's typical to write so that the numbers are first and the variables are afterwards. So this is what I explained. Note here that here it's not 100, it's 100,000. The point is that in this side we measure with grams, so we should measure with the same unit on this other side also. So it was 100 kilograms, which is of course the same as 100,000 grams. And if you look at the sugar, protein, water, spice constraints there, they obviously come from here. So you see that this tabular form is really convenient. The only difference is that here on the right hand side I've just used the unit of the left hand side. So for example, in the spice melange it's milligrams here on the left hand side, so on the right hand side it should be milligrams also, which is just multiplied by 1000. And luckily it's actually multiplied by 1000 for every one of them. All right, so that is how we got these constraints. Maybe still another point about these units. So as I said, the units in each line, so each line is its own constraint, they have to be the same on the both sides. I mean, this is, you have to compare the units with the same units, otherwise it kind of doesn't make too much sense. But in some sense these constraints are independent. It means that in different lines you can have different units. So suppose, for example, that for the protein, let's go back here, the protein we decided to use the kilograms on bottom side. So in that case we would have a 150 kilograms here, and here 0.28 kilograms, 0.18 kilograms, and 0.05 kilograms. So what happens if we do that? Well, in practice nothing happens. I mean, we can do it. So then this would be the constraint. This one here would replace the protein constraint, this one here. But if you look at them just as inequalities, never mind where they come from, this inequality, so this side is less than or equal to this side, is exactly the same as this inequality, except that there is a small typo. This should be extreme. Sorry about that. I try to remember to fix that typo. Okay, why are they same? So if you take this inequality here, the protein inequality, and divide both sides by 1000, you get this. And this is, I hope that you have all learned this from school, that if you have an inequality and you multiply or divide both sides with a positive number that's not 0, then it's the same inequality, nothing changes. Okay, so we are basically finished with this LP modeling. So here is the model. Just remember the sign constraints. So this is that we are actually selling the cakes, not buying them. Again, this was not explicitly stated in the problem, but I think it was implied. And yeah, that's the LP. A final note is that, yes, let's look at the problem that's given like this here, and let's open the old notes or the Octave notes, and there let us look at the chapter 4, which was the same problem in slightly different manner presented. Let me scroll down and up. All right. Yes. So I just want to make this a sort of a, sorry about all these windows. Okay. So that was the problem 4.1, which was the same as our 5.1. And this is the kind of, I was actually deliberately gave this problem in a very annoying form. So this is just to encourage you to present your problems, or when you have a problem, to rewrite the problem in a way where all the problem data is somehow collected together and hopefully in a nice, beautiful form. And tables are nice and beautiful. You can, or it's of course, your sense of beauty may differ, but at least for me, if I see a problem like that, and then there is a list of here, and then there are numbers here and there, I mean, it will just annoy me to collect all the, see what happens where. But if I'm given the same thing in this tabular form, I will immediately see what's going on, and I already actually get a pretty good idea. Well, idea about the solution, not the solution itself. All right, that was the video lecture about Chapter 5, Product Mix Problem Revisited, and the modeling part of the product mix problem. Hope you enjoyed. See you in next videos. Bye bye.